Hey guys, welcome to 9.2 binomial theorem. We're gonna expand out the binomial a plus b for our warm-up. A reminder that a plus b is a binomial because there's two terms, a and b, as opposed to monomial with one term or a trinomial with three terms and so forth. So a plus b to the 0 is 1. Hopefully that's self-explanatory. Even more self-explanatory, a plus b to the first is just a plus b. A plus b to the second, well, some basic algebra is applied here, but first we can write the expanded form or the factored form. And here we distribute a, and a would be a squared. A times b is ab, and b times a is ab again, so we have two of those, so that's plus 2ab. And then b times b is b squared. I'm leaving a little space there on purpose so that we can take a look at how this leads to binomial theorem. A plus b to the third, we have some of the work done because if we were to write this as a plus b times a plus b times a plus b, well, in there is a plus b squared, so I can leave this a plus b, but we know that we've done this already from the work right above it. So let's distribute the a plus b to the a plus b squared part of the polynomial. So a times a squared would be a to the third. A times 2ab is 2a squared b, plus a times b squared is just ab squared. Now we got to distribute the b. So plus 2a squared b plus 2ab squared, and then the final multiplication would be plus b to the third. A to the third and b to the third are unique terms, but we have some like terms in here, a squared b and a squared b, and we have three of those, so plus 3a squared b. And then we also have ab squared, again we have three of those, so 3ab squared. Now, if you can look at this right now, and I'm not done marking it up yet, so there's some missing symbols and some spaces, but as you can see, every time I raise the exponent from 0 to 1 to 2 to 3, the amount of work goes up exponentially, right? The amount of number of steps, the number of times I have to distribute, it goes up exponentially. So what we want to do is we want to figure out a pattern, because we really don't want to go a plus b to, let's say, the 10th and have to do this by hand. The only way around that, if we're going in this route, is to just brute force sit there, and it's tedious, it's monotonous, and basically impossible if we want to have this done in practical applications of probability, which leads to statistics, and that's what binomial theorem is about. This entire section is trying to figure out or show how we can do this with higher powered exponents without having to do all of this tedious work. So this warm-up basically leads to what we're looking at with binomial theorem if we just simply did this. Now, what I just did there, obviously, is I made my answers wrong, right? I can't just throw in a B and an A there and expect it to be correct, because obviously that changes the value of whatever this expression is supposed to represent. So what can we do? We can put in this, right? I've essentially multiplied those little monomials in there by 1, because b to the 0 and a to the 0 are just 1. And the reason I'm doing this is because this is where binomial theorem, the patterns in which it's that are leveraged to come up with an algorithm to do high-powered binomial expansion, this is where it starts. I'll see you in the next video with that, because that might be, just a few minutes on its own.